For our second interesting example of applications of differential equations, we will look at virus propagation, or if you want to put it another way, disease simulation. Now, I've been talking about this for years, and I actually quite enjoyed it, and we had good fun with students. Then the COVID came, which took some fun out of it, but hopefully this is all behind us, and we can have fun with this example again. So let's have a look at it. We have some population of people, and we have some disease, and some people are infected. So IT, that will be how many people are infected. Now, to take into account that you have populations of different sizes and so on, it's actually better to see this as a proportion. So these are infected people, proportion. So this number is taken from the range 0, 1. If I is equal to 1, then everybody is infected. Now, apart from infected people, you have to have also some people who are susceptible. Let me check. Yeah, I think that's the right one. Again, this is a proportion. And these are people who are not infected yet, they are not sick yet, they are healthy, and they are capable of contracting the disease. Okay? Now, the simplest model that you can think of is exactly based on these two groups. It's called SIS model. How does it work? You are healthy, you meet somebody who is infected, you contract it with some probability, you get sick, you are sick for a while, then you get healthy again, and you can again join the game. So from infected, you again become susceptible. Typical example is the common running nose, common cold, I think they call it, whatever, okay? Annoying, but yeah, you can live with that. So SIS model, how does it work mathematically? We will start with the infected people. So the derivative. How does the group of infected people change? Well, it gets larger if somebody who is infected meets somebody who is susceptible and successfully transmits the disease. Now, for that, we have to go to people from probability statistics, and they tell us that when you have proportions of people, and that's the advantage of having proportions, if you have proportions of some groups and you multiply them, then you essentially get the probability that they meet within a specific time interval. So I multiply I by S to essentially show the chances of their meeting, and I multiply it by some constant beta, which fixes the probability to be exactly the right number, and also includes information about the disease. How contagious is it? Because every time infected person meets susceptible, it's not quite sure that there will be a successful transmission. It depends on many factors, and one of them is, let's say, the danger, how dangerous the disease is, how quickly it jumps from one person to another. Okay, so we've got increasing numbers of infected people, but after a while they get healthy again and they leave this group. Now, this is actually tricky. Because, for instance, when you take common cold, when you contract it, when you get it, it usually lasts about 3 to 7 days, and then you get healthy again. So there is a time interval involved, but this is impossible to capture in the form of a differential equation. So we do something else, which is not exactly the same, but okay. We will say that a proportion of infected people gets healthy again. Actually, I should use gamma here. Okay, that's the traditional constant. There are some traditions for denoting different factors in the medical field, so I will try to follow them. So gamma is the constant which describes how readily infected people get healthy, which means that they become susceptible again. That's the SIS circle. Okay, that's the equation for the changes of the infected people. Now we look at the susceptible group. Now, because there are just two groups, it's quite obvious that every time somebody moves from one group to another, it influences both of them in the same way. So here we see people moving from S to I, and therefore they are actually leaving the group S. And these are people who are moving from group I to group S, so they are enlarging the group S. And that's it. This is the system of differential equations for the SIS model. Okay, before we look at some picture, let's talk about it. First of all, I can see I times S. product of two unknown functions. This is not a linear system, unfortunately. Otherwise, the situation would be much easier. It's not a linear system, but we are used to the fact that interesting systems are not linear. That's life. What can we say about them? Well, we had this video about analyzing systems. Let's ask some good questions. For instance, are there any stationary solutions? Good question. Well, could it happen that the derivative of I is equal to 0? And because they are essentially the same, those derivatives, just with opposite signs, this is actually enough to also figure out that the derivative of s is 0. Well, I look at this formula, and I can notice that I can factor out I. So I'm really asking, I times beta s minus gamma, could it be 0? And I also notice that there is no t in the equation, so it's autonomous system, which is wonderful. Okay. Are there any values of I or s that would make this left-hand side 0 regardless of time? Definitely. One possibility is when I is equal to 0, and then, of course, s is equal to 1. How do I know? Because these are the only two groups. So s plus I must be 1. Well, you have a population and nobody is infected. Well, then nobody gets infected in the future either. That's a stationary situation. Wonderful. Okay, we can see another possibility. When s is equal to, and let me think about it, in order for this to be 0, s has to be gamma divided by beta. And this number is not 0. So this is an interesting situation, and it's not 1 perhaps either. We have to be careful. For some settings, this is not possible. We have to make sure if this number belongs to 0, 1. Then we have this special stationary solution. And then, of course, for I, we get the complement to 1. 1 minus gamma over beta. So there are actually two stationary solutions. One of them is obvious, and the other one is not obvious, but yeah, it seems that there is a balance where in this mechanism of people moving from one group to another, these two streams of people, there is one stream going one direction, another stream going the other direction. There is a specific situation where those two streams are the same, and then those two groups, they become stable. Okay? Now, we could inquire about stability of these two equilibria. And this takes some work. We could, for instance, look at these expressions and ask what happens if I am near this stationary situation and I shift a little bit away. How does this derivative look like? Does it bring me back or not? Things like that are possible. Let me just tell you that this one is unstable. So when you have a community and you introduce some infected people in it, there is a low probability that you will get back. It depends on those parameters, beta and gamma, but typically this is unstable. So let me just put it, okay, in the brackets like that. Typically unstable. Okay, let's have a look at some pictures. So this is a system of differential equation for SIS model, and when I look at it, beta Si minus gamma I. I couldn't use I, okay, so don't get distracted by IN here. IN is infected. If I used I, Maple would think that this is a complex unit, a constant, okay? I had to be careful. Gamma, gamma, beta, yeah, everything works well. So let's have a look at some results. Here we go. I chose some constants which I found in some medical journals. So they are, okay, they are not constants of some particular disease, but I sort of put them so that they are nice numbers, but reasonable, close to some real-life diseases. And what we see here, again, we have to be careful. We have three quantities now: time, the number of infected people, the number of susceptible people. And we can only choose two quantities to show at the same picture. So we have time on the horizontal axis, and on the vertical axis, I can see the number of infected people. So in this particular scenario, I started with 20% of infected people, and after a while, the situation stabilized at about 70% of infected people. By the way, if you try to play with it, you will find that this stationary solution is stable, typically. So this is a nice typical picture for a stable situation. Let's have a look at another picture, the same settings, the same beta and gamma. And now we can see actually two graphs merged. One graph is the number of infected people in red. The blue curve, that's the number of susceptible people, which essentially means healthy people. And we can see that together they should give 1, and when we look at the numbers they do, it's a nice stable situation. How does it look like if I look at the orbit? And the answer is, it looks like this, and the arrows are actually quite useful because you can, it helps you to read the orbit. If I didn't put the arrows there, it would be difficult to interpret. Let's have a look at the initial conditions. I have them somewhere here. So the initial conditions are that the number of susceptible people is 0.8, so 80% of people are healthy, and 20% of people are infected. And you can see it over here. We start at 0.2 proportion of infected. Now let's find it in the orbit picture. Let me run it again. So on the horizontal axis, we can see the number of susceptibles, vertical axis, the number of infected, and at the starting point, we have 20% infected, 80% susceptible. That's this position. Okay, so at this point, we are at time 0, and the arrows suggest that we move in direction to the upper left corner. So as the time goes, the proportion changes in this way. So the number of susceptible people is getting smaller, and number of infected people is getting larger. And it is a straight line because these two quantities add up to 1. So it must be a straight line. And now here is the location which was actually the limit. That was the stabilized situation. So in a limit, we would get here in the orbit and just stay there. So we can see that there is a vertical line over here at which opposite arrows meet. So these are possible situations where different initial conditions stabilize. Now, this is actually interesting. The fact that s plus I is equal to 1 means that the starting positions can be only along this oblique straight line, connecting number 1 here and number 1 here. So on this straight line, we can have the only permissible starting conditions. And when you look at it, you can see that no matter where you start on this line, the arrows will always move you towards this point. So all initial conditions eventually end up here, and that's most likely this stationary solution. I would say that it's stable based on the picture that I see. Now, there are also some other pictures, but unfortunately, they are just pictures for differential equations without taking into account that s plus I must give 1. Okay? So these are not realistic. These are like mathematical virtual realities which are not connected to our situation. Now, I mentioned that the behavior of the system depends on the constant beta and gamma. And as it turns out, and you can see it over here in the picture, they are not really important as such, but the ratio is important. So I'm going to keep gamma and change beta a little bit. Now remember, beta is the probability that when two people meet, they will transmit the disease. So beta in this picture, in this experiment that I have, is 0.5, and gamma is 0.15. So the chances of transmission are higher than the chances of getting healthy again, in a way. That's interpretation. Let me try to change beta to 0.15, and let's see how it changes the dynamics of the disease. So now the probability of getting healthy is much strengthened compared to probability of contracting the disease. And let's see how this whole vector field changes. And it changes totally, because now all the arrows are going down towards the lower corner. And remember, we are only allowed to be on this oblique line. So no matter where we start on this oblique line, which starts at 1 and goes all the way down to 1, no matter where we start, our orbit will keep going in this direction to the lower right corner, and it stays there. So this suggests that it's actually impossible for this community to keep some disease in it, disease of this type. So if the transmitting power of the disease is lower, then the community, even if somebody brings it there, defeats this disease, which is wonderful. That's what we want. Let's have a look at this. Notice that if beta is the same as gamma, then S is equal to 1. That's the other stationary solution, but it's actually the same as the first one. So there is just one stationary solution when everybody is healthy. No other stationary solution in the game. And it's reflected in this vector field. We can see it over here. And this brings one to an interesting question. Can we somehow help society so that it works like that with all diseases? Which brings us to inoculation. Inoculation simply makes it sure that this is the picture for the disease that we fear really a lot, Okay, we'll talk about it a little bit later. So that's the SIS model. Let's have a look at our second model. It's called SIR. Again, these are three groups, proportions that add up to 1. And the R group, these are people who do not want to play the game anymore. These are so-called removed. And as I said, this is going to be a proportion. Now, it's not just about groups, but also about how people move from one group to another. For the SIS model, we can see a merry-go-round. You've got group S, group I, and people move both ways. In the SIR model, the situation is somewhat different. You've got people in susceptible group, and they move to the infected group, and these move just to the removed group. There is no going back to S from R in this model. That's the end. So there's just one directional flow of people. How does it go? Well, the infected people, they are gaining new members of the club by meeting susceptible people with some probability of transmission. And they are losing members at a specific rate. Again, it would be better to somehow incorporate time constant, but that's not possible. Now, it's traditional for the SIR model to use a different letter here. Let's call it nu. This is, let's say, less popular. Everybody knows gamma. Nu, okay, that's a letter, another Greek letter. How about susceptible people? Now, they are just losing members. They are losing them to the infected group. And they are not gaining any new members, while the last group, removed, keeps gaining new members from the infected group. So that's the system. And you look at these three equations and you ask, are there any stationary solution? And the last equation tells you right away that there's only one possible stationary solution. And that is when the number of infected people is 0. And at that moment, all these derivatives become 0. And then you do not really care about the number of susceptible and removed people in the population. By the way, removed people, how do you become removed? How do you say, I don't want to play the game anymore? Well, essentially two possible ways. One of them is that you get the disease and you become immune after you get healthy. And when you are immune, you are not susceptible at all. The other way is that you get the disease and you die. And then you cannot get it again, so you are removed from the game. When we talked about proportions, in order for the mathematics to work well, we are not allowed to change the population size in the middle of the experiment. So we have to keep the population size stable, and when somebody dies, we simply move them into this special group. Now, for the purposes of the model, it's actually the same thing if you die or if you get healthy again and get immunity. These are the same things. The model doesn't care, which is sort of curious because we usually do, but that's mathematics for you. Okay, just one stationary solution. Is it stable? I don't think so. We will see. Once you introduce some infected people, again, it depends on the constants. You may want the diseases to die out again, so you want this to be stable. But typically, for many diseases, this is not true. Okay? So that's another thing to talk about. Now, before we look at pictures, there are 3 unknown functions plus time, which makes 4 quantities that we may want to see. One possibility is to make a separate graph for each function, as it depends on time, and perhaps overlay these 3 graphs. This could tell us something. Or we can choose any pair of functions and show an orbit for them. Let me start with this orbit business. So over here, I set up the system for my SIR model. And now for some constants, again, these are reasonably truthful constant or reasonably realistic. What we can see over here is the orbit. On the horizontal axis, we can see the number of susceptible people. And on the vertical axis, we can see the number of infected people. So where do we read it? How do we read it? At the start, 99% of people were susceptible. So the whole population was healthy. And there was 0.01% of people infected. So it's just like you have population of 10,000, which is a huge city, and one infected person comes in. Nobody was immune or dead at the start. Okay? So the starting point is over here. Almost everybody is susceptible, nobody is infected. And as the time goes, the number of infected people was going up and the number of healthy people was going down. And it was kept going down all the time. So the number of healthy people was steadily decreasing. But also here, the number of infected people is decreasing. So at the end, it seems that everybody moved to the group R, removed. And let's hope that these are all guys who are healthy and they get immunity. That's the ideal situation, ideal outcome. Okay, here we go. 3 graphs. Here we can see them. The blue curve, that's the number of susceptible people. The red curve, that's the number of infected people. And we can see how the number of infected people shoots up and then goes down in time. And everybody moves to the black curve, which is the removed people. So we sort of guessed it right. And let's face it, you would guess this even without knowing any mathematics. If somebody told you, okay, this is the mechanics. People are healthy, then they get sick, then they get healthy again, and they have immunity. So what will be the development? Well, you would guess something like that. So this is not really surprising. Let's use this opportunity to review a little bit about numerical mathematics. How does it work for the Runge-Kutta methods? We are essentially working with 3 graphs at the same time. Here we have time, and here we have infected people, susceptible people, removed people. We start with some initial data. Nobody is removed, almost everybody is susceptible, and there is few infected people. We split the time axis into chunks of equal size to make our life easier. So there is a step size h. And now notice that we know at time 0 the values of r, s, and I. We can substitute them here, and when we substitute them here, we get the slopes. And when we know the slope and the position, we can do the tangent line. So we form tangent lines, and for the slope, we use exactly this formula. So this will be the initial value plus the derivative times h. And the derivative we substitute from here. And similar formula works for all the other guys. Initial value plus the derivative times h, and so on. And you move simultaneously all of them, because you have the initial data, so you can substitute, change all of them, get to a new place. And once you get to the new place, you can again take this information, substitute to the right-hand side, you get the slopes, and you can make simultaneously the next step. And you keep going like that until you get to the end. Okay? So that would be the Runge-Kutta approach. And if you decide to do it in an easy way, this is actually the Euler forward formula. I may try to do more journeys and try to find some balance, Runge-Kutta order 2, 3, 4, and you can play with it a little bit. Once you have a formula for the slopes, you are in business, of course, for all Runge-Kutta methods. So let's try just something simple, and I'm not going to call on any procedure. I just program it manually. Little implementation of the Euler method for this situation. So I chose the horizontal step size to be 10, and I will be interested in time horizon 100, let's say, seconds, whatever. And there is some initial conditions which I borrowed from the previous example, from the one that we can see on the top. And now there is a simple code which starts at the initial value, which is the previous one, at time k minus 1. Then it substitutes into the formula for the derivative of infected people. And when we compare it, we can see beta, we can see s times I, which is this, and we are subtracting constant times I. Yeah, so these are exactly these formulas, and they are multiplied by horizontal step size. So I really just took these formulas, substituted for derivative, and programmed them like that. And I make a loop, and then I just visualize the outcome. Here we go. Well, is it? Well, negative number of susceptible people, this does not quite sound good. So this is obviously not very good, but the general shapes are okay. But that's because I used a really huge step size. You can see it here, those segments on time axis, they are really huge. So let's try something more reasonable. Let's say step size 1. That sounds good. Wow. Now let's compare it with the picture here. Yeah, we are essentially there. So these Runge-Kutta methods, they really work. And it wasn't difficult. I just programmed a few lines of code. Okay? So that's very, very nice. By the way, our motivation is to make this group R as large as possible so that the infection doesn't have any room to play. You can become a member of group R by getting sick, then getting healthy, and having immunity, by dying, or by getting vaccinated. If the vaccine is safe, and if it works, that's the best way to become the member of group R. And essentially, using this model, you can figure out the constants beta, nu, and so on. This can be obtained from data on people. How many people are sick at different times, how many people are healthy, and so on. You look at the dynamics, and you can actually get estimates of these constants. And based on these constants, you can figure out how many people in population, again, we talk about proportion, how many people have to be vaccinated so that if disease comes, it dies out on its own. You remember the picture when all the diseases went to zero? All the cases? Well, that's exactly what we want to do. Now, depending on how the disease is contagious, this proportion of people that need to be vaccinated can be rather small or rather high. So there are some diseases for which if you vaccinate like 60, 70% of people, then this disease can come from outside and then it dies on its own. And you're fine. For some diseases, they are so bad that you need to vaccinate something like 95% of people if you want to be sure that if the disease comes from outer space, it will die out on its own. Okay? So these are really interesting things. Of course, it's assuming that this vaccination is actually a vaccination. Typically, when you say vaccination, you mean something which you get, and then for the rest of your life, you are safe. So there are vaccinations like that, and for those, these models really work well. Okay, we need one more example over here. This is SIRS model, which essentially, again, if I draw pictures, draw arrows, you are susceptible, you get the disease, you become removed by getting immunity and surviving the disease, and then after a while, this immunity wanes and you become susceptible again. Let's see. Now, if you understand how these previous equations came about, this should be easy. Let's see. Infected people. They are gaining new membership from the susceptible people, and they're losing membership to the removed group at a specific rate, omega. The susceptible people, they're losing membership to the infected group, and they're gaining new members, constant gamma, from the removed group. And finally, the removed group is gaining new membership from the infected people and losing numbers to the susceptible group at a rate which is proportional to how many people are removed yet. So this is a new model. Let's just quickly look at some illustrative pictures. And again, these pictures are what one would expect. So it seems that for at least some interesting combinations of parameters, again, the situations tend to stabilize. We can see here all three curves in one picture. The number of infected people shoots up, that's the red curve. The black curve, the number of removed people. And it seems that in this particular situation, it's also possible for a part of population to survive, even though they do not have immunity and they were never sick. So all kinds of situations can happen. These models can be used to, let's say, predict what will happen, to influence our actions. They have one big problem, they are simplified. And we actually talked about it over here. In many cases, the transfer between different groups is not based on probability, but on time interval. So for instance, immunity lasts half a year and then you lose it. You are infected for 2 weeks and then you get healthy. And this actually requires a different approach to model accurately. And if you are using these models, you shouldn't trust them all that much. You should be aware of the fact that they are not all that faithful. There are models which are better, which take into account this time interval problem, but they are done in a totally different way. Agent models, things like that, discrete models, much more work, totally different part of mathematics. Before we go, the difference between these models can be actually very important, for instance, for zombie apocalypse. Traditional point of view at zombies is through the SIR model, which means you are healthy, you get bitten by zombies, you become a zombie, and then you have to be removed, otherwise you are around forever. So this is the traditional approach, but there are some books, some movies which actually look at it as a SIRS model, because they assume that if you are a zombie, you can actually become healthy again. The removed may mean that you are somehow healed. So these are interesting things. They are much more complicated models with M group and so on. A lot of fun, but we are out of time essentially. Let's move to something totally different, a third example.